Hi, I'm Jayson and we're going to be talking about Coulombs Law today. So way back when, there was a man named Charles Augustin de Coulomb, and he was really interested in how charged particles interact with each other. He noticed that as charge collected on one particle, it could either repel or attract another particle. And nowadays we know that we can either have positively charged particles or negatively charged particles. And so he noticed that when there were two oppositely charged particles, those tended to be attracted towards each other. And there was a force somehow bringing them together. And then also if he had two positively charged particles, then those particles would repel with a similar force. And so he wanted to figure out a way to somehow measure this, somehow predict the force that would happen between two charged particles. So he noticed first of all that he has the force, and if we increase the charge of one or both particles, then the force between them increases as well, whether that be the force to drive them together or the force to drive them apart. So he noticed that, if we have the charge 1 and charge 2, Q standing for charge, as we increase one or both, we also get an increase in force. He also noticed that as he brought, let's say, two positively charged particles together, as the distance decreased, the force between them increased. Or inversely, for a positively and negatively charged particle, if you bring them closer together, if you decrease the distance, then the force attracting them also increases. So if we put that into the equation form, we can say that as the distance decreases, then the force is going to increase. So we divide those charges divided by the distance, R standing for distance. And so after some experimentation, he discovered that the relationship is more like the distance to the power of 2. And then also we need a constant just to bring everything together. So that constant actually is something that's very important. It's equal to 8.99 times 10 to the 9 newtons meters squared divided by coulombs squared. And so we'll see why we have those units in the practice problems. But this is the equation that he designed for this Coulomb's force, this Coulomb's law. And through the practice problems, we'll be able to understand how we can apply this knowledge. So in this problem, we're going to have two charges. We're going to have one charge right here and another charge 10 centimeters away. So the distance between these two is 10 centimeters. So charge 1, we're going to call this charge 1, has a positive charge of 2.5 microcoulombs. And then the charge on the second charge, we're going to call this charge 2, has a charge of negative 4 microcoulombs. And so we want to find the force between these two charges. So if we remember from previously, we have Coulomb's equation, which is the force between two charges is equal to K times the absolute value of charge 1 times the absolute value of charge 2 all over R squared. Alright, so we know charge 1, we know charge 2, we know the distance, and so we should be all set. So K is equal to 8.99 times 10 to the 9th. And then the units on K are equal to newtons meters squared per coulomb squared. So the reason that we have those units like that is so that in the end we're just going to be left with newtons, which is the unit of force. And so then we have times charge 1, which is 2.5 microcoulombs, times charge 2, which is negative 4 microcoulombs. We're running out of room there. And then that's all going to be over 0.1 meters squared. We got to make sure to change those centimeters to meters so that we can use them in this problem. And so we also are going to change these microcoulombs to coulombs. So down here we have 8.99 times 10 to the 9th newtons meters squared over coulombs squared times 2.5 times 10 to the negative 6 coulombs times negative 4 times 10 to the negative 6 coulombs. That's all going to be over 0.1 meters. We're going to square that value. And so now if we solve that, we're going to get 8.99 times 10 to the 9 newtons meters squared over coulombs squared. And that, all of this together, 2.5 times 10 to the negative 6 times negative 4 times 10 to the negative 6, take the absolute value of that, that's going to give us 1.0 times 10 to the negative 11 coulombs squared. And that's because we multiplied this coulomb by this coulomb. And so as you can see, those coulombs squared are going to cancel out with the coulomb squared that we got from the K. And then that's going to be over 0.01 meters squared. Which you can't see that very well. There we go. And so this meter squared is also going to cancel out. And so if you multiply all those values out and solve for the force, we're going to get 8.99 newtons. And that's going to be the force in between these charges. If you can remember, we have a positive charge here and a negative charge here. And because opposite charges attract, that's going to be an attracting force between those two charges. So we're going to get 8.99 newtons pulling those two charges together. Alright, in this second problem, we're going to have two positively charged particles, and they're going to be repelled by a force of 90 newtons, and these two charges are separated by a distance of 1 centimeter. And so what we want to find out in this problem is the charge of these two particles. Now these two particles have the same amount of charge. So first we're going to set up our equation. So we have the force is equal to the absolute value of charge 1 times charge 2 over r squared. And of course we don't want to forget the Coulomb's constant in there. And so we know that the force is going to be 90 newtons. And we know K to be 9 times 10 to the 9, and that's newtons meters squared, almost wrote coulomb squared, over coulomb squared. And then that's going to times by Q1 times Q2. And because we know that Q1 is equal to Q2, we can just say that that's going to be Q squared. And then we're going to divide that by the distance, which is 1 centimeter. So we want to change that into meters. So we have 0.01 meters. We're going to square that. And so in solving for this problem, we're going to want to solve for Q here. So we have 90 divided by 9 times 10 to the 9 newtons meters squared over coulomb squared. Notice how the newtons cancel out. And then we're also going to multiply that by 0.0001 meters squared. And the meters squared cancels out as well. And so we're going to just simplify all that out. And that's going to be equal to Q squared. Take the square root of both sides. And we're going to end up getting Q to be equal to 1 times 10 to the negative 6 coulombs. And so that basically tells us that these two particles both have a charge of 1 times 10 to the negative 6 coulombs to give us the overall force of 90 newtons.